Hello fellow hams and YouTubers. Well, we're back on the bench for this video. I've done a few computer videos, you're probably getting bored with those, but we're going to build something today. Back in the early days of ham radio, amateurs were truly amateurs and they built their equipment. It was common to have a receiver, some kind of shortwave receiver, and put together your own transmitter, a single tube oscillator basically. And a lot of people started out that way back in the day. Well, that's still viable today, and I think everybody should at least build themselves one transmitter. They're very simple to make. If you want a low power QRP transmitter, very easy to make, just a handful of components, and you can actually make a contact. About the only thing you might have to source would be one of these, a crystal. Now, you can get on eBay, and I have found a plethora of crystals for the 40 meter CW portion of the band really cheap. This happens to be 7.122 megahertz, really common, and there's also 7.037, I think, or 038, somewhere down there. There's a real common one, but you can find them across the 40 meter spectrum. Some good areas for slow CW would be 7.05 to 7.055 if you find something in that range, or 7.01 to 7.02 or 22. Or 7.1 to 7.122. You know, anything in those ranges would be good, because all you really need is an oscillator that's going to put out RF and maybe one little stage of amplification to get a little bit more power out of it. So we're going to build a simple two-stage CW transmitter. Let's go to the bench. So here's the circuit that I've settled on for my low power transmitter. It's pretty straightforward. These are 2N2222 transistors, the really common NPN transistor. This one comprises a crystal oscillator. I believe that's called a Colpitts oscillator. I'll have to verify that. I might have the wrong name in my head, but minimal component count. You've got these two capacitors are identical. They are 150 picofarad. And then this resistor that provides a turn-on voltage to the transistor is 47K. Yep, 47K. And this R2 is 1K. And so as the transistor turns on and off, we get a feedback loop through the crystal. There's a 40 meter crystal. And an oscillation, which is then coupled over here to this transistor, which is basically just a power amplifier. L1 is a choke that chokes RF off from coming back up to the power rail. R3 is the turn-on bias for the transistor, and that's 33K. And then R4 was not in the original design. The original design, the emitter went straight to ground, and I found that the output signal was badly distorted. It wasn't a sine wave. It was two mixed frequencies. This was starting to, I don't know if this was oscillating or what, but it was a very distorted output. So this is only 22 ohms, and that provided just enough current limiting to clean up the output signal, make it a perfect sine wave, which is then the amplified signal is then coupled through C4, which is a 0.1 microfarad. Oh yeah, coupling from the oscillator to the power amp is C3, which is a 0.01 cap, 0.01 microfarad. 0.1 microfarad, and then we have our low-pass filter. This oscillator is going to create harmonics, 1 in 14 megahertz, which is the 20 meter band. So this low-pass filter will pass the 7 megahertz signal, but attenuate the harmonics. And C5 and C6 are identical. They are 475 picofarad. And L2 is 14 turns around a small toroid. I'll show you that in a moment. I think the toroid is about a half an inch, maybe 3/4 of an inch in diameter, outer diameter. So that's the transmitter, crystal oscillator power amplifier. The circuit draws about 84 milliamps at 13 volts when it's keyed on, which wattage power equals current times voltage. So 13 times 0.084 gets 1.092. So it's dissipating about 1 watt of power. Now, I don't know how much of that's making it out to the antenna, but it's dissipating 1 watt of power. So, so who knows? Maybe we're getting 200 milliwatts, maybe we're getting 300 milliwatts, maybe half a watt. I'll have to figure it out after I put it on an antenna and see what the meter shows. So I have breadboarded the circuit up here. Ignore the Arduino. It lives on that half of my breadboard for future experiments. I'm just using this left half of the breadboard. So that's the completed circuit breadboarded up. I got my oscilloscope probe hooked up on the output of the low-pass filter. And I've got over here my meter to monitor current when I kick it on. It starts out around 65 milliamps and then that rises as the transistor heats. So really on for Morris it's going to be drawing about 65 milliamps on key down, which would be, quick calculation, 13 times 0.065. So it's dissipating 845 milliwatts of power when it's initially keyed down. Now you can see that's rising up. It'll stabilize around 84 milliamps. So up here on the scope, there's a scope. I'll turn it on. And we got a nice, we got a nice clean sine wave on the output. 4 volts peak to peak at, well, the scope's counter fluctuates, but it's actually 7.122 megahertz, exactly what the crystal is. So that's our output. Now, if I put the scope into FFT mode, so we can see, there's our, there we go. Okay, this is the fundamental. That's the second harmonic, that's the third harmonic, there's the fourth harmonic. And you can see that second harmonic is way down, right? Now I'm going to put the scope on the input to the low-pass filter. Okay, and there you can see that second harmonic is just about a quarter of the fundamental. So that low-pass filter is making a big difference. I'll put the scope back on the output. There, see the difference? There's our fundamental, and there's our secondary harmonic, which is now less than half, or about half what the fundamental is. So, yeah, that low-pass filter is working really well. So that is my transmitter. Now it's just breadboarded. So I'm going to build it onto some PC board. I got a nice little PC board to build it onto. And then it's tricky drilling the Altoids tin, but this is what it's going to go in. That'll fit. That'll fit in there just fine. So that's what I'm going to do tomorrow, is I'm going to rebuild that little guy into the Altoids tin with a transmit receive switch and an antenna input and an antenna output for the receiver. And then we'll have a complete station, ultra low power, on 40 meters, and we'll see if we can make a contact. So for the transmitter, we're going to need 2 toroids wound. One is the RF choke that feeds the power to the final amp, power amplifier, and that is 6 or 7 turns on a single core. I'm using, I think this is a 18 gauge wire, magnet wire. Now this one is the inductor for the output filter circuit, the low-pass filter. This is a 17 millimeter, or well, I measured it just a little bit ago. It's about 17 millimeters core, 18 gauge wire, and you need 14 turns on here. Now, winding toroids scares a lot of people off from projects. And I'll tell you, if you just start at the end with the wire and run all the wire through each time, it's a little tedious, but it's really quite easy. What I do is I'll take the wire and I'll start with the wire right in the middle, halfway through. All right, and then I will wind half the turns in one direction around the core, and then take the other end and wind the rest of it in the other direction. That way I'm only working with half the wire at a time. It's a little bit easier. So I'm going to wind 7 turns around this side, and then take the other end and wind another 7 turns in the around the other side. So I'll have 14 turns total. 2, 3, and you just put the wire through, pull it through, make it nice and tight, and you want to try to space those turns out somewhat evenly. The more even they are, the more consistent the inductor is going to be. So that's 1, 2, 3, 4. 5. And I'm pinching the wire with my fingers and holding it there. And after I bring this through, I kind of use the tip of this index finger to hold that wire in place while I bring the end around and through again. 1, 2, 3, 4, 5, 6, 7. All right. Now I'll just flip this around, and I'll take the other end and do 7 turns in this direction, and then I'll have my 14 turn inductor. There, so now I got 14 turns around the toroid, and then I'm just going to carefully spread them a little bit so that they are all about evenly spaced out. Totally spaced out, man. And we're done. So it's really not that hard to wind. And then we just have to cut off the excess wire. And this is magnet wire, so it's insulated with varnish, a kind of varnish. I've got some sandpaper here, and I'm just going to go and strip the insulation off the ends of the wire so I can push it in the breadboard or solder it, make connection to it. So I'll do that on both wires, get them nice and shiny copper, and then my inductor for the output circuit, output low-pass filter will be done. So that's it. It's pretty easy to wind a toroid. I'm going to put the transmitter in an Altoids tin. Gee, what an idea. Whoever thought of that, huh? How many times have you seen that done? But what I had to do was plan it out, and I had to think about where I was going to put everything and how I'm going to hook it up and get all the connectors together. So I have 2 RCA panel mount connectors. This one over here is going to be for power coming in, 12 volts to 13 volts in. I figured RCA was, well, it was what I had available, and it's good enough for power. So I'll use that for power in. This RCA jack will be the receiver antenna out. This is the transmit receive switch. So this will feed out to my receiver, optionally. And what it will do is when I put this into transmit mode, it will ground the receiver's antenna so that the receiver doesn't get overloaded by the RF coming out of the transmitter. Also, when I put this in transmit mode, it will complete a path from the transmitter board to the tip on the key connector, which is what this 1/4 or 1/8 inch jack is. This is going to be for the Morse code key. And then the shell of the jack contacts the shell of the Altoids tin and completes the ground. So the transmitter board will ground through the switch when it's in transmit mode to the tip on this jack, and that will enable the transmitter. So when this is in receive mode, there's no path to ground on the circuit board and the transmitter is disabled. So I've got everything figured out where I'm going to put it all. I've got roughly the size of the board figured out. I'm going to cut this down about that thick, I think it should fit. And it'll sit in the Altoids tin, allowing space for the jacks and connectors. Planning, you know, you got to think about these things, figure out how you're going to do it, and then start assembling it. Now, the next step is going to be drilling holes in the Altoids tin and mounting all the connectors. That's a really fiddly, tricky thing to do. These are so thin that they are really hard to drill. It's too easy to bend them, or the drill will snag and catch and just tear the metal. So I'm going to measure this, and I'm going to cut a couple of pieces of wood that I can put in there to support the sides while I drill it. And then the trick on drilling this really thin tin is to start really small, real small hole, and then work your way up until you reach the size that you need the hole to be. The biggest one is going to be the BNC antenna jack. So that one's going to take the most drills to work it up to the size and get that mounted in there. So. All right, well, the tin is prepared. As you saw, all the jacks are mounted, switches and everything. It's all thought out, how it's going to work. And the way I'm going to wire it, since the code key is plugging in here and the receive antenna is plugging in here, I'm going to wire the switch so that that way is receive and that way is transmit. See, it's a visual cue. Flipping it towards the key input will be transmit. Flipping it towards the receiver antenna output will be receive. So that'll be a nice visual cue. So that's the tin all sorted out and ready. Now it's time to start on transferring the circuit from the breadboard to the PC board. So this this always takes a little while. It's always a pain kind of trying to think about how to route things. And I have to consider where the jacks are in here and how I'll be wiring to the jacks for antenna, power, ground line to the key. Yeah, got to think about all that while I'm wiring up the circuit board and lay the circuitry out appropriately. A lot of times, well, at least in this case, the way the schematic is drawn, the circuit just moves left to right, oscillator and then power output. And so it kind of makes sense to physically lay it out on the board that way, with the oscillator on the left, power amp towards the right, except that the antenna is going to be on the opposite side, so it might make more sense to flip it around and put the oscillator on the right, power amp towards the left, because the antenna jack is going to be over here on the left. So I think that's what I'm going to do. Well, that's the oscillator circuit. Looks nice and neat, doesn't it? Now the power amp. And there is the completed transmitter. All laid out. All right. Well, now I've got ground, power, and I need to put a wire over here on the into the output network for the antenna lead coming out, and that'll be all the wiring on the board. Then it's just a matter of installing it into the Altoids tin and wiring all that up, and we'll be done. We'll be ready to test it out. Well, look at that, a ham radio project in an Altoids tin. Never would have thought of that, would you? That's what everybody does. But anyway, it is all wired in, all hooked up, all ready to go. I just need to make a power cable for it and a antenna cable. No, I got that. Got the key jack. I just need to make a receive antenna patch for my Grundig receiver and a power cable. And then I'll be ready to take it upstairs and try her out. She's ready to go. Well, here we are. We've got our simple CW transmitter right here in the Altoids tin. And I've got it hooked up to my external antenna. This receiver output is coming to this Grundig Global Traveler receiver. Power and the homemade code key here. So we'll turn the radio on, the receiver, and I've got it tuned to 7.1225 megahertz, which is where my oscillator is going to put out, and I don't hear anything. So I'll flip my transmit receive switch to transmit, which grounds the receiver antenna and enables that. We'll still hear the transmitter in this when I key down. See, so it's putting out power. So let's call a CQ once or twice and see if we get anything. I might be at this a while. W9 GT. Oh, he's running 500 milliwatts. That buzziness on this receiver is a nearby broadcast station mixing in with the received signal. Comes and goes. Well, there we go. We made contact. Now Jack is just a few miles away, but he was also running a low power transmitter that he built. He said 500 milliwatts. This is probably 100 or 200 milliwatts, and he gave me a 579. Yeah, 579. So he got a pretty good signal from me. So there we go. We just made contact with this little tiny transmitter. Thanks for watching. If you enjoyed the video, don't forget to give it a thumbs up. Also, if you're not already a subscriber, click to subscribe. Join us on the Facebook channel for discussion about the videos. And if you'd like to help support this channel, please click to support me on my Patreon page.